Okay, nice, thank you. Hello everyone, I'm Joscha Jahns. I'm also part of the Lise Meitner group at this institute that is led by Laura Spittler. And I will talk about our observations with this beautiful telescope on the right when it was still among us. Yeah, it's a collaboration with all the people that you see down there, especially with the group around Jason Hassel's at Amsterdam. Yeah, and we were monitoring the FRB 121102 with the Arecibo Telescope over several years and once to twice a week. Yeah, but before I go further into our results, I want to give a brief introduction. Most of this has already been discussed in previous talks, so I think I will go quickly over it. Like in this diagram, you can see the width against the luminosity, and FRBs are at exactly the same width as pulsars or magnetars, but they are much more luminous because they are far away and still visible. Yeah, otherwise the differences from FRBs to magnetars are that FRBs are single pulses usually, that only are observed once. They are often narrowband. This is not always, but repeaters are typically narrowband. And then the few repeaters that we know of, they don't show any, well, they show periodicity. Two of them show periodicity, but not at the small time scales that pulsars are. And lastly, they are extragalactic. Yeah, we already heard about SGM 1935 that bridged the gap between these. It's really hard to see here, but it's like still 3 orders of magnitude below the luminosity of FRBs, but it's yeah, it's a galactic magnetar that was really bright. And here it is seen that it was coincident with a gamma ray detection. Yeah, observed by 2 radio telescopes at the same time, slightly preceding the gamma ray. Okay, and we have seen these kind of plots already as well. This is from Mikili 2021, where we have some quasi-periodicity in FRBs. So these 3 are FRBs and not galactic sources. Okay, so but I promised you to talk about this FRB 121102. And it collected a lot of these juicy firsts. It was in 2014, the first one that was not discovered by Parkes. It was the first repeater that was discovered, and it was the first FRB that was localized to its host galaxy, small dwarf galaxy. Yeah, but it's also interesting in many other aspects. First, it has incredibly high RM. There's a RM of 10 to the 5 rad per square meter, which is, well, the only other sources that have this high RM are from the galactic center. So, and yeah, there was also an ATEL last week which reported that this source has now decreased by around 70% in the last 6 years. So that's also an incredible change. Okay, yeah, and Koustup had already shown this plot. I think, yeah, this is the periodicity of this FRB, which is around 160 days with about 100 days activity, and then 60 days of non-detection. Okay, so we monitored this FRB because it's very interesting with the Arecibo Telescope. And yeah, one of the outcomes is presented in this study. It's the, I think, most active phase of this FRB, the November rain 2018. We found 850 bursts in 10 observations only, and you can see the family portrait here of the brightest bursts. Yeah, you can see a lot of interesting things. You can see that some of them are very wide, while others have very sharp, spiky structures here. You can also see the Saturn bone that Marlon already mentioned, this downward drift in frequencies, and you can actually see it in, I would say, in all of them. Yeah, and yeah, it's called Saturn bone because it always goes down and never up. And yeah, it's the same for this one. Yeah, so first, again, an overview over these 10 observations. So first we detected a few bursts. In brackets, we bracketed it kind of in the active phase that was reported by Cruces et al. And then we saw two observations that had no bursts, and then we saw large activity reaching over 200 bursts per hour. And so this gave us a very good sample to do some statistics. Yeah, and I'm going to talk about two in particular, two analyses. One is the wait time. Wait times are the times between consecutive bursts, and they are very promising, but not so widely used in pulsar studies. Yeah, I mean, if you see a pulse every period, it's a bit boring. So for this, it's much more interesting. So the dot plot is from FRB 121102, the one that I analyzed, and you can see in white the expected wait time distribution if they arrive randomly. So if you have a Poisson point process, you see this exponential distribution in white, and you can see that most of the wait times do arrive randomly, but we have the second peak here, which is a mix of subbursts. So let's go back. So subbursts, I mean, like subbursts are different components of the same burst, so they are naturally close together. But then there's also in the same peak, there's also some that appear to be different bursts, but are very close together and do not follow this randomness. Yeah, but particularly it's also interesting what we don't see. So I want to compare it with the results of Marlon with from the magnetite that he just presented. And yeah, things that we don't see in our FRB are, for example, the periodicity that is super clear here. And the white stripes here are the first is the periodicity, the second one is the two times the periodicity, three times the periodicity, and so on. You can very clearly see these peaks from that. And the second thing that you can also see here, which we don't see up here, is the gap in between, which is the phase where the magnetite is not bursting. So we can say that there's not, at least not such a large time where the magnetite is not bursting, or the FRB is not bursting at all. Okay, so all right, great. The second thing I want to talk about is our spectral temporal analysis. We fitted these 2D Gaussians to all of the bursts that we had, and tried to fit every component with such a 2D Gaussian, and use that to analyze the spectral temporal structure. So in very short, the result is that our interpretation of the result is that the Saturn-Bonn effect is also affecting the burst, the smaller bursts. Let me explain more. So what we see here is that sharp bursts are very straight, and wider bursts are inclined. And yeah, the reason for that is that not only the burst centers drift in the Saturn-Bonn, but the whole emission within the burst drifts as well. And we detected this also within the shortest bursts. So I like this plot and the next plot because it's showing this intuitively, I hope. So let's see. So the dispersion, if you would de-disperse only this burst, if you would only see this one component, you would over de-disperse it, right? So we can give an equivalent dispersion measure to this inclination, and that's what's plotted here. So for wider bursts, you would see them, you would falsely detect them at a higher dm. And this is plotted here against the width of the burst. And the shorter the burst, the smaller is this effect. Yeah, and the reason, as I already said, is that this is probably coming from the Saturn-Bonn effect, and it's going down all the way to the shortest bursts. They are all affected by this. So it biases our dm, but this plot clearly shows that it is an intrinsic effect from the FRBs. Okay, so explanations are because we interpreted it in terms of the Saturn-Bonn effect, the explanations are also kind of the same that we use for the Saturn-Bonn effect. The first, one of them is the radius to frequency mapping. So if FRBs come from the magnetosphere of magnetars, then we have this radius to frequency mapping, so that some emission that comes from closer to the magnetar is at higher frequencies, and emission from wider out is at lower frequencies. And since there's a small delay between these, we get this Saturn-Bonn effect. Yeah, and a second possibility that I also wanted to mention is that it can also be explained in relativistic shocks that are also one possibility of FRB emission. Yeah, and then I'm already coming to the summary. I think I'm just going to leave it like this. All this is published in end of the last year in this paper, Jahns et al. 2023. Yeah, thank you all.
Questions? Lucy?
Hi. The Saturn-Bonn effect, I mean, you mentioning it biases the end, which of course was rapid with frequency. Is the Saturn-Bonn effect sort of very confidently a linear frequency thing, or is it still sort of looser?
It's not, no, it's not confidently. In our data, we cannot really decide if we fitted a linear slope, but it's not necessarily. For example, the relativistic shock models predict some index around 1. I think between 1.9 and 3, and we cannot exclude it. There was one version seen by, I think it was a chime burst as well, like almost all of them, which showed this feature that it seemed to have this effect, but it was very quadratic. So, yeah.
That's all right. So in the radius to frequency mapping concept is the idea that it's this small time delay, but they're so far away that over the distance that you'll get the frequency difference, or I don't know, why would you see that in FRBs but not in?
Well, that I'm not sure.
What's that from there?
Also, can I do it's about this one?
Okay.
So in R3, the other repeater, it has downward drift, and there it's the linearity extends all the way from 1.4 gigahertz with average to 150 megahertz with low firing for storm. So even on a decade time scale, decade frequency scale, it's linear.
Roger?
Yeah, so on slide 11, I think where you showed the 2D version.
Yeah.
So I was just curious about this third question which you put inside. I was just wondering how significant that is, because
Yeah, it's in the 2D, it doesn't look super significant, but here
biased by RFI.
in the top here you can see that it's quite,
Okay.
it looks like it's there. Like, and if you
And the inclination is
if you fit only this one and then you subtract and you look at this residuals, then it's more clear. But yeah, I agree, in this plot it's not very clear. Yeah.
One last question from the back.
So there is this idea that the repeating FRBs share a common power law for drift rates. So do you compare your drift rates with other repeating?
We didn't look so much at the drift rates. This would be something for the future. But yeah, this has been done in other studies more. Yeah, by yeah, it would be interesting, especially to do that over larger frequencies. That has partly been done.